In 1945, a mathematician at Columbia University opened a storage drawer and found something impossible. The clay tablet measured roughly 13 centimeters across, its surface covered in wedge-shaped marks pressed into dried mud nearly 4,000 years ago. Catalogue number Plimpton 322. The curator's notes said it came from somewhere near ancient Lhasa in southern Iraq, purchased decades earlier from a dealer whose records had long since vanished. But it was the content that stopped the mathematician cold. The tablet contained a table of numbers, not simple counting, not basic arithmetic. It displayed 15 rows of calculated values showing Pythagorean triples, sets of whole numbers satisfying the relationship between the sides of right triangles. The kind of mathematics that wouldn't officially exist until the Greek philosopher Pythagoras developed his theorem over 1,000 years later. Except here it was, already complete, already sophisticated, already assuming the reader understood advanced trigonometric concepts without explanation. There were no practice tablets showing how Babylonian scribes learnt this, no simpler versions, no mathematical exercises building toward this level of complexity. Just this, fully formed, precisely calculated, professionally executed. As if the scribe who pressed these cuneiform characters into soft clay already possessed a complete system of mathematical knowledge and was simply recording a small piece of it. The tablet had been broken. Its left edge was missing, suggesting it once contained even more information. What remained showed calculations accurate to several decimal places, rendered in the base 60 numerical system that would eventually give us 60 seconds in a minute and 360 degrees in a circle. The precision was remarkable. The implications were troubling, because if this represented the Babylonians' level of mathematical knowledge around 1800 BC, where had it come from? Where were the centuries of development? Where were the mistakes, the false starts, the gradual refinements that characterize human learning? The tablet sat in that drawer like a message from a civilization that had skipped straight to the answer without showing its work. And Plimpton 322 wasn't alone. Across museums in London, Berlin, Paris, Philadelphia and Baghdad, storage rooms held thousands of clay tablets inscribed with knowledge that seemed to have no origin story. Medical procedures that wouldn't be rediscovered for millennia. Astronomical calculations requiring centuries of precise observation. Chemical formulas for materials we struggled to reproduce with modern equipment. All of it emerging in ancient Mesopotamia within a span of centuries so brief it barely registered on the timeline of human civilization. But here's what the tablets don't usually mention in museum displays. Some of that knowledge disappeared. Capabilities documented in earlier periods simply vanished from later texts. Techniques described in 3rd millennium Sumerian tablets were absent from 2nd millennium Babylonian records. Technologies mentioned matter-of-factly in one era became lost arts in the next, as if someone had erased specific chapters from humanity's instruction manual. This isn't speculation. The tablets themselves document the disappearance. Later scribes copying older texts would add notes. The meaning of this word is no longer known. Temple libraries contained formulas for materials no one could make anymore. Medical texts reference procedures no living physician understood. The Mesopotamians themselves were aware they had lost something. Tonight, we're going to examine what those losses might have been. Not the famous Sumerian inventions we celebrate, the wheel, writing, cities, law codes. Those stayed. We're looking at what the cuneiform texts reveal about capabilities that appeared, were used, and then vanished, leaving only fragmentary descriptions and the haunting suggestion that ancient scribes were preserving knowledge they no longer fully understood. Before we go further, I'd appreciate if you'd leave a comment mentioning where you're listening from and what time it is there. There's something profound about people scattered across the world, across time zones, all exploring the same ancient mystery in the quiet hours. It connects us to those long-ago scribes who also stayed up late, pressing reed styluses into clay, trying to preserve what they feared might be forgotten. The air in museum storage rooms has a particular quality: cool, dry, controlled. The kind of environment that stops time, or at least slows its corrosive passage. In these vaults, clay tablets rest in archival boxes, each one a frozen moment from a civilization that vanished 3,000 years ago. The tablets are surprisingly heavy, dense clay, deliberately fired or accidentally hardened when the buildings housing them burned. Some are no larger than a smartphone. Others require 2 hands to lift comfortably. Plimpton 322 has a warm earthen colour, the kind of brown-orange clay that speaks of desert rivers and alluvial plains. Under magnification, you can see where the ancient scribe's reed stylus pressed into the surface, leaving tiny ridges along the edges of each wedge-shaped mark. The pressure was firm and confident. This was someone who wrote cuneiform, the way a modern accountant fills spreadsheets, routine, professional, unburdened by doubt. But what the scribe recorded wasn't routine at all. The numbers on Plimpton 3E2 demonstrate knowledge of what we'd now call trigonometry, the mathematics of angles and triangles that forms the foundation of everything from architecture to astronomy. The tablet shows the scribe understood the relationship between the sides of right triangles, not just practically, but theoretically. This wasn't someone who knew that a 3-4-5 triangle made a right angle because they'd measured it. This was someone working from principles, generating new Pythagorean triples mathematically, understanding why the relationships held. Modern scholars examining the tablet have identified that it likely served as a teaching aid or reference table. But teaching what and to whom? If this was educational material, it implies students who already possessed significant mathematical literacy. You don't hand trigonometry to beginners. The tablet assumes its users already speak the language of advanced mathematics, which means somewhere in ancient Mesopotamia there existed an educational system capable of producing mathematicians who could work comfortably with concepts we now associate with high school or university coursework. The tablet sits in its archival box, labelled and catalogued, a piece of humanity's intellectual history preserved by accident and soil chemistry. But it poses a question that whispers through those quiet storage rooms. What else did they know? If this fragment of a broken tablet demonstrates this level of sophistication, what knowledge was recorded on the millions of tablets that didn't survive? What was written on the section of Plimpton 322 that broke away and crumbled into dust? And perhaps more unsettling, if the Babylonians of 1800 BC possessed this mathematical knowledge, why do later tablets suggest some of it was forgotten? The problem of appearance. The Sumerians appeared in southern Mesopotamia around 4500 BC, though appeared may not be the right word. They were there, farming the flat alluvial plain between the Tigris and Euphrates rivers, developing the irrigation agriculture that would eventually support cities. For thousands of years, their culture evolved gradually, building on what came before in the way human societies typically do: slow accumulation, incremental improvement, generation after generation, adding small innovations to inherited traditions. Then, around 3500 BC, something changed. Within the span of roughly 3 centuries, a geological eye blink, Sumerian civilization exploded into complexity, not in one area, but across multiple domains simultaneously. Writing emerged from simple pictographs to a full syllabic system capable of recording abstract concepts. Cities grew from villages to urban centres, housing tens of thousands. Temple architecture evolved from simple shrines to massive ziggurats. Metallurgy progressed from basic copperworking to sophisticated alloying. Mathematics developed from counting to positional notation and complex calculations. Astronomy moved from casual observation to systematic record keeping that would track celestial patterns across centuries. This pace of change was extraordinary. Scholars call it the Uruk period, named after the city that epitomized this transformation. But period suggests a natural phase of development, when what the archaeological record actually shows looks more like a sudden threshold crossing. Before 3500 BC, we have villages and pottery. By 3200 BC, we have bureaucratic city-states recording grain shipments in cuneiform, tracking astronomical observations, smelting bronze, and building monuments that required engineering calculations. The conventional explanation holds that population density and agricultural surplus created conditions for specialization, allowing some people to become full-time craftspeople, priests, and administrators. This is certainly true as far as it goes, but it doesn't quite account for the sophistication level. It's one thing to say surplus wealth allowed for specialists. It's another to explain why those specialists immediately demonstrated advanced capabilities in their fields. Consider the earliest proto-cuneiform tablets from Uruk, dated to approximately 3200 BC. These aren't tentative first attempts at writing. They show a fully functional accounting system with standardized symbols, consistent sign forms, and complex numerical notation using different base systems for different categories. Base 60 for most counting, base 10 for some measurements, specialized systems for tracking grain, beer, and livestock. This represents not just the idea of writing, but a comprehensive information management system deployed across an entire administrative apparatus. The tablets from this period number in the thousands. They document a functioning bureaucracy, tracking resources, labour assignments, and distribution. The scribes who produced them wrote with confidence and consistency. But where were they trained? Where are the practice tablets showing students learning the system? Where are the developmental stages where earlier, simpler notation was tried and refined? Some exist, certainly. Archaeologists have found token systems that preceded cuneiform, small clay shapes representing quantities of goods, sometimes sealed in clay envelopes. These show gradual development over centuries, but the leap from three-dimensional tokens to two-dimensional notation in the tablets happened rapidly, and the tablets themselves show remarkably little variation or experimentation. It's as if the system was designed, implemented, and standardized within a generation or two. The same pattern appears in mathematics. The Sumerians used a sophisticated sexagesimal base 60 number system. This wasn't a simple choice. Base 60 is mathematically elegant because 60 is highly composite, evenly divisible by many smaller numbers, which makes fraction calculation enormously easier. Working in base 60 allows you to represent 1/2, 1/3, 1/4, 1/5, and 1/6 as clean, non-repeating fractions. Try doing that in base 10. But who designs a number system? Who sits down and thinks, we should structure our counting around a base that optimizes fractional arithmetic? That requires understanding the mathematical properties of different bases before you've even built the system. A chicken and egg problem that suggests the Sumerians either possessed remarkable theoretical insight or inherited the system from earlier mathematicians whose identity has been lost. Their astronomy presents similar puzzles. By the early 2nd millennium BC, Babylonian astronomers were tracking the movements of Venus with precision, predicting planetary positions, and calculating eclipse possibilities. This requires not just observation, but systematic data collection across generations. You can't predict celestial events from a few years of watching the sky. You need decades or centuries of records to identify the patterns. The Babylonians had those records. Their astronomical tablets reference observation series stretching back into periods we have no other documentation for. They cite data points from eras before the tablets we've found were written, implying an unbroken tradition of systematic sky watching that preceded even the earliest texts we possess. Who started that tradition? Who convinced the first observers that tracking star positions night after night, year after year, would eventually yield useful patterns? In metallurgy, the Sumerians were producing bronze, an alloy of copper and tin, by 3000 BC. Bronze making isn't intuitive. Copper and tin ores don't naturally occur together. The metals have different melting points. The proportions matter crucially for the alloy's properties. Too much tin makes the bronze brittle. Too little provides minimal improvement over pure copper. The ideal ratio, around 10-12% tin to copper, has to be discovered through experimentation. But the earliest Sumerian bronze shows they already understood optimal ratios. There's minimal evidence of trial and error in the archaeological record. The bronze artifacts from early periods demonstrate metallurgical competence that should have taken generations to develop, yet it appears in the record already mature. The same holds for their architectural knowledge. The ziggurats required understanding of load-bearing walls, foundation preparation, and the behaviour of brick structures at monumental scales. The temple of Inanna at Uruk, built around 3200 BC, stood on a massive platform requiring thousands of bricks and precise engineering. Building something that size without collapse demands knowledge of weight distribution, settling, and structural integrity. Where did that engineering expertise come from? Scholars studying Sumerian origins encounter what's informally called the Sumerian problem. The Sumerians themselves appear abruptly in the archaeological record without clear predecessors. Their language isn't related to neighbouring peoples. It's not Semitic like Akkadian, not Indo-European, not related to any known language family. It stands alone, linguistically isolated, spoken by people who left no clear trail of migration. Their own texts offer little help. The Sumerians themselves claimed their knowledge came from the Anunnaki, beings they described with terminology that scholars translate as gods, but which literally means something closer to those who from heaven to earth came. Were these metaphorical explanations, mythological frameworks for understanding civilization, or were the Sumerians recording their own understanding of knowledge transmission, describing wisdom inherited from teachers whose identity later cultures reframed as divine? The texts don't present knowledge as invented through human ingenuity. They present it as gifted, taught, or revealed. The god Enki, associated with wisdom and fresh water, is credited with giving humanity the me, a concept usually translated as divine powers or civilization's elements, but which the texts describe more like templates or principles. Enki doesn't inspire humans to figure things out. He provides the actual knowledge, fully formed. This framing appears across Sumerian literature. When cities are founded, the texts don't describe trial and error. They describe the correct procedures being followed, as if consulting an existing manual. When technologies appear, they're presented as gifts from divine teachers rather than human innovations. This could be mythological retconning. Every culture creates origin stories. But it's worth noting that the Sumerians themselves didn't claim to have invented what they knew. They claimed to be preserving and applying wisdom that preceded them. Modern archaeology tends to interpret this as cultural humility or religious devotion, not literal historical claim. But what if we took the Sumerians at their word? Not about gods and divine beings, but about the core assertion. What if they genuinely understood themselves as preservers and transmitters of knowledge systems they had inherited rather than originated? That would explain the sudden appearance of sophisticated capabilities. It would explain why the earliest examples of Sumerian writing, mathematics, astronomy and metallurgy show minimal developmental fumbling. It would explain the absence of clear innovation sequences, because they weren't innovating, they were applying. But if that's true, then from whom did they inherit this knowledge? And what happened to the earliest civilization that developed it? The tablets themselves offer no direct answer, but they offer something else. Traces of discontinuity, references to techniques no longer practiced, names for materials no longer identified, copies of older texts with annotations admitting the copyist doesn't understand the terminology, evidence that the Sumerians themselves were at times working with knowledge they only partially grasped, as if they too were inheriting fragments of something older, trying to preserve what they could before it vanished completely. What the clay remembers. The preservation of Sumerian knowledge was an accident of geology and catastrophe. Clay tablets are durable but not indestructible. Unfired, they can crumble back into mud with moisture exposure. Fired deliberately, they become nearly permanent, but firing takes time and fuel that would have been expensive for everyday administrative documents. Most Sumerian tablets were left unfired, dried in the sun, intended for temporary records of accounts and inventories that would matter for a season or a year before being recycled back into clay. What preserved them was fire, specifically the fires that destroyed the buildings containing them. When cities burned, whether through warfare, accident, or conquest, the flames that consumed wooden roofs and furnishings baked the clay tablets as effectively as any deliberate kiln. The same conflagrations that ended libraries and palaces inadvertently immortalized their contents. We owe much of our knowledge of Mesopotamian civilization to destruction. The tablets lay buried for millennia, protected by accumulating soil and the region's dry climate. When 19th century excavators began digging into the tells, artificial mounds created by successive layers of human habitation, they found thousands upon thousands of inscribed clay pieces. Early diggers didn't always recognize their significance. Some tablets were discarded as rubble, others were taken as souvenirs, their provenance and context lost forever. The systematic archaeological excavation that would eventually recover tablets, with careful documentation of their find spots, came later, after decades of less careful digging had already dispersed many artifacts into private collections and museums worldwide. Decipherment of cuneiform was itself a detective story spanning decades. The script had been dead for nearly 2,000 years when European scholars first encountered it in the 17th century. Early investigators copied inscriptions from visible monuments in Persia, recognizing that the wedge-shaped marks were writing but unable to read them. The breakthrough came through multilingual texts, particularly the Behistun inscription in modern Iran, a massive rock carving commissioned by Persian King Darius I around 520 BC, written in Old Persian, Elamite and Babylonian. British officer Henry Rawlinson risked his life copying the Behistun text from the cliff face in the 1830s and 1840s. The Old Persian portion could be partly understood through its relationship to known languages. Using it as a key, scholars gradually worked out the cuneiform signs for Babylonian and eventually for the older Sumerian language underneath. By the 1850s, cuneiform was yielding its secrets. One of the great moments in decipherment came in 1872 when George Smith, a self-taught Assyriologist working at the British Museum, was translating tablets from Nineveh. He came across a tablet describing a great flood, where a man was warned to build a boat to save his family and animals. The similarity to the biblical Noah story was so striking that Smith reportedly became so excited he began removing his clothes, a perhaps apocryphal detail, but one that captures the astonishment of discovering that ancient Mesopotamian literature contained parallel narratives to texts considered uniquely Hebrew. That tablet was part of the Epic of Gilgamesh, and its flood story predated the biblical version by over 1,000 years. But more importantly, it demonstrated that the clay tablets contained not just administrative records and raw propaganda, but literature, mythology, and accounts of events that multiple ancient cultures had independently recorded. The tablets were memory itself, preserved in mud. Since Smith's time, hundreds of thousands of tablets have been excavated, catalogued, and translated. The majority are mundane: grain receipts, worker rosters, tax records, loan agreements, and property disputes. But embedded among the bureaucratic records are treasures, medical texts, mathematical exercises, astronomical observations, ritual instructions, magical incantations, proverbs, poetry, and descriptions of procedures. Some tablets are tiny, no larger than a postage stamp, recording a single transaction or calculation. Others are substantial, covered with multiple columns of dense text. Many are fragmentary, broken pieces that may be part of larger works, leaving tantalizing gaps in the narrative or argument. Museums house jigsaw puzzles of scattered fragments, and occasionally scholars successfully match pieces separated by decades of excavation and thousands of miles of museum collection dispersion. The texts reveal a civilization intensely concerned with preservation. Scribes routinely copied older tablets, generation after generation, maintaining libraries of knowledge. In Ashurbanipal's library at Nineveh, excavated in the 19th century, archaeologists found tablets that were already ancient when the Assyrian king's scribes copied them in the 7th century BC. Some texts came with colophons, statements at the end identifying the scribe, the date, and the source. These colophons sometimes note that the tablet is a copy of an older text from before the flood, a phrase that recurs with unsettling frequency. What did before the flood mean to Mesopotamian scribes? For some, it clearly referred to the mythological deluge described in their epics. But the phrase appears in mundane contexts too. Medical texts, mathematical tablets, ritual instructions. These weren't epic poetry, they were procedural documents. And the scribes treated them as historical records from an earlier era, not mythological fables. Some tablets contain annotations by later scribes who clearly didn't understand what they were copying. Marginal notes say things like meaning unknown or ancient word, not in current use. This is remarkable. The scribes were preserving texts whose content had become partially opaque to them, maintaining documents whose full meaning had been lost even as they carefully reproduced the signs. This suggests a culture aware of its own knowledge erosion. The scribes weren't simply maintaining a living tradition, they were engaging in conscious preservation of information they recognized as valuable even when they couldn't fully interpret it. They were trying to prevent knowledge from vanishing completely, even if they could only save the words, and not always the understanding. Some texts explicitly lament this loss. A tablet from the 1st millennium BC, copying an older medical text, includes a note from the scribe. The plant names written here are in the ancient language. I have written them as I found them, though their identifications are no longer certain. The scribe knew he was transmitting incomplete information, but he transmitted it anyway, hoping perhaps that future readers might recover what his generation had lost. This raises a profound question. If Mesopotamian scribes in the 1st millennium BC were preserving texts they didn't fully understand from before the flood, what were those original texts preserving? Were the Sumerians themselves, at the dawn of cuneiform writing around 3200 BC, already engaged in preservation rather than innovation? Were they recording knowledge systems that predated writing itself, translating oral traditions or pictographic systems into the new technology of cuneiform script? The earliest proto-cuneiform tablets show remarkable standardization. They don't read like experiments in creating notation. They read like implementations of an already designed system. Someone decided what symbols would represent what concepts, how numbers would be written, how tablets would be organized. That design work had to happen before the first tablet was inscribed. But we have no records of that design process. We only have the finished product deployed across multiple cities simultaneously. It's as if the Sumerians sat down one day, with a complete writing system already worked out in their minds and simply began using it, which suggests the system itself, not just the act of writing it down, came from somewhere, from minds that had thought through information storage and retrieval, from a tradition that understood the principles of symbolic notation. The clay tablets are artifacts of memory-fighting entropy. Each one represents a moment when someone decided this information mattered enough to record. But they also represent all the information that wasn't recorded, all the knowledge transmitted orally, all the techniques learned through apprenticeship and observation that left no written trace. The tablets are fragments of a larger corpus that we can now only glimpse, and some of those fragments describe capabilities that later disappeared, leaving us with descriptions of practices no one continued, formulas for materials no one made anymore, references to knowledge that survived as words without meaning, echoes of a more complete understanding that time had, eroded until only its shadow remained pressed into clay. Mathematics without ancestors. In the Yale Babylonian collection, under catalogue number YBC 7289, sits a small circular clay tablet, roughly 9 centimetres in diameter. It's immediately distinctive. Most cuneiform tablets are rectangular, but this one is round, designed to fit comfortably in one hand. The tablet dates to the Old Babylonian period, approximately 1800-1600 BC, and it contains a diagram that would look familiar to any geometry student, a square with both diagonals drawn. Numbers are inscribed along the sides and across one diagonal. The horizontal side shows the number 30 in sexagesimal notation. The diagonal bears two numbers, 1,024,051,010 and 42,25,035 in the same base 60 system. To modern readers trained in decimal notation, these numbers seem arbitrary, but when converted they reveal something extraordinary. The first number on the diagonal, 1,024,051,010, represents approximately 1.414213 in decimal form, an accurate calculation of the square root of 2 to within 1 part in a million. The second number is the product of this value and the side length, confirming the diagonal's length. This wasn't an approximation derived from measurement. This was a calculated value accurate to 5 sexagesimal places. For perspective, the square root of 2 is an irrational number. Its decimal expansion continues infinitely without repeating. There's no simple fraction that captures it exactly. Modern calculators give it as 1.41421,356. The Babylonian value on YBC 7289 matches this to 1.41421,296, accurate to the 6th decimal place. The scribe who inscribed this tablet nearly 4,000 years ago had access to either a calculation method or a reference table that computed square roots to exceptional precision. This matters because calculating square roots isn't intuitive. It requires algorithmic thinking, following a systematic procedure to refine an approximation through multiple iterations. The Babylonian method, as best scholars can reconstruct it, involved choosing a guess, dividing the target number by that guess, averaging the result with the original guess, and repeating until convergence. This is essentially the algorithm still taught in numerical methods courses. It works reliably, but requires understanding that iterative refinement can approach irrational values with arbitrary precision. Who discovered this method? How many generations of mathematicians refined it before it appeared on YBC 7289 as a routine exercise? Because that's what this tablet appears to be, a teaching example, something produced by a student or used in instruction. It's not presenting new mathematics, it's demonstrating established knowledge, which means the method was old enough, well enough understood, and widely enough taught that it had become pedagogical standard material. YBC 7289 isn't unique. The Yale collection alone holds multiple tablets demonstrating sophisticated mathematical techniques. YBC 7290, another circular tablet from the same period, shows calculations for the area of a square using the diagonal. Plimpton 322, which we encountered at Columbia, contains a table of Pythagorean triples that requires generating values through systematic calculation, not just recording discovered integer relationships. These tablets reveal that Babylonian mathematics operated at two levels simultaneously. On one level, it was practical. Surveyors used geometry to measure fields, architects calculated material quantities, administrators tracked grain storage volumes, but on another level, it was theoretical. Mathematicians explored numerical relationships for their own sake, developed general methods, and pursued precision beyond practical necessity. Consider the sexagesimal system itself. Working in base 60 is not intuitive for humans with 10 fingers. Every culture that independently develops counting naturally gravitates toward base 10 or base 20, reflecting finger counting. Base 60 is a conscious abstraction, chosen for its mathematical properties rather than anatomical convenience. It suggests the Sumerians inherited or developed their number system through deliberate analysis of what base would optimize calculation, rather than through natural counting evolution. The advantages are considerable. In sexagesimal notation, fractions like 1/2, 1/3, 1/4, 1/5, and 1/6 all have finite representations. These fractions, troublesome in base 10 where 13333, become clean in base 60, 1/2 or 30, 1/4 15, 1/5 12, 1/6 10. This makes astronomical calculations, which involve dividing circles into parts, enormously easier. But it also requires users to memorize multiplication tables significantly more complex than those required for base 10. A complete sexagesimal multiplication table must include products up to 5959, yielding 3481 distinct products. For comparison, base 10 multiplication requires only 81 products up to 99. Learning to calculate in base 60 represents a substantial cognitive investment, only justified by the long-term payoff in computational efficiency. The Babylonians made that investment. Their mathematical education system produced scribes fluent in sexagesimal arithmetic, capable of complex calculations involving multiple operations. And these weren't just elite specialists. The tablets show that numerical literacy was widespread enough to support routine commercial and administrative functions across society. What's missing, however, is the origin. Where are the tablets showing the transition from simpler counting to base 60 notation? Where are the proposals and debates about which base to adopt? Where are the educational materials for the first generation of scribes learning an entirely new numerical system? They don't exist in the archaeological record. The sexagesimal system appears in the earliest Uruk tablets already functioning. It's not marked as new or experimental, it's just there, being used competently by scribes who clearly consider it normal. The same absence characterizes the geometric knowledge. Tablets like YBC 7289 demonstrate understanding of the Pythagorean theorem over 1,000 years before Pythagoras, but they present it without fanfare, without attribution, without any indication that this represents an achievement worth celebrating. It's routine, expected, the kind of thing student scribes practice, because of course calculating diagonals is something competent mathematicians do. This suggests the knowledge was already old when these tablets were inscribed. The scribes weren't discoverers, they were practitioners of established methods, trained in techniques their teachers had learned from earlier teachers in an unbroken chain that stretched back to some foundational generation whose identity had been forgotten or perhaps never recorded. Some tablets hint at this ancestry. Occasional colophons reference ancient mathematical series or note that a calculation follows the old procedure. These phrases imply the scribes recognized they were using methods from earlier periods, but they don't explain where those methods came from or who developed them. One intriguing pattern appears in mathematical tablets from different periods. Earlier tablets, particularly those from the Old Babylonian period like YBC 7289, demonstrate higher precision and more sophisticated techniques than later tablets from the Neo-Assyrian and Persian periods. There's a decline in mathematical achievement visible across the archaeological record. Later mathematicians possess less knowledge than earlier ones. This isn't how technological progress usually works. Mathematical knowledge, once gained, tends to accumulate. Theorems remain true. Methods remain valid. Each generation should build on the previous one's achievements, adding new discoveries to the inherited foundation. But the Mesopotamian tablets show erosion. Techniques documented in 3rd millennium tablets are absent from 1st millennium texts. Precision achieved in Old Babylonian calculations isn't matched in later periods. What caused this regression? Wars disrupted cities, conquest dispersed scholarly communities, economic collapses ended institutional support for scribal education. But these were temporary disruptions. Why didn't the knowledge recover? Why didn't later civilizations in the same region restore what had been lost? One possibility is that the knowledge had always been fragile, maintained by relatively small communities of specialists. When those communities dissolved, their expertise went with them. Mathematical knowledge requires continuous transmission. It's not enough to have tablets containing formulas. You need living teachers who understand the principles well enough to explain them to students. You need active practice to keep techniques sharp. You need institutional structures, schools, libraries, patronage systems that value and support mathematical work. If any link in that chain breaks, knowledge vanishes surprisingly fast. A technique that a generation considers routine can become incomprehensible to their grandchildren if it's not actively taught. The tablets remain physically preserved, but the understanding evaporates. Later scribes copy the symbols without grasping the concepts behind them, creating hollow shells of knowledge, correct words without comprehension. This may explain the annotations on some late period tablets. Ancient calculation method, meaning uncertain. The scribe could copy the notation, but couldn't perform the calculation. The procedural knowledge had been lost, even as the symbolic record remained. But this raises a deeper question. If knowledge erosion can happen so easily, happening repeatedly across Mesopotamian history as documented in the tablets, how did the original sophisticated knowledge arise? How did the first Sumerian mathematicians develop techniques advanced enough that their degraded remnants, after millennia of partial transmission, still exceeded what most other contemporary civilizations achieved? YBC 7289 sits in its archival box, a hand-sized circle of clay with numbers pressed into its surface. It's a teaching tool, a student exercise, a piece of everyday mathematical practice from 1800 BC. But it preserves a calculation accurate to 6 decimal places for an irrational number. It demonstrates knowledge that would vanish from human mathematics for over 2,000 years before being rediscovered. And it offers no explanation for where that knowledge came from, only the finished product, only the answer precisely calculated, pressed into clay by a scribe who had learned it from someone who had learned it from someone in an unbroken chain, stretching back to a beginning the tablets never describe, as if the mathematics, like the civilization that used it, had simply appeared one day, already complete. The physicians who should not exist. In the University of Pennsylvania Museum, among the extensive collection of tablets excavated from ancient Nippur, sits a document catalogued as part of the museum's cuneiform holdings. Dating to approximately 2600 BC, this tablet contains what scholars recognize as the oldest known pharmacopoeia, a collection of medical recipes and treatment instructions. What makes it remarkable isn't just its age, but its content. The tablet describes medical preparations with specificity that implies systematic understanding rather than trial and error folk medicine. It lists ingredients, including alkali, salt, plants later identified as varieties of willow and myrtle, and compounds requiring multiple processing steps. It provides procedures: crush the dried plants, dissolve in beer, allow the mixture to settle, strain through cloth, apply to the affected area. These aren't vague recommendations, they're precise formulas that specify proportions, preparation sequences, and application methods. They describe extraction techniques, dissolving active compounds in liquid carriers, filtering to remove solids, concentrating solutions through evaporation. This represents understanding of basic chemistry, that certain substances contain active principles that can be separated from inert material, that solvents can extract desired compounds, that purification improves efficacy. The Sumerian physicians who used this tablet didn't just know these treatments worked, they knew how to prepare them reliably, which implies they understood something about why they worked. This is sophisticated pharmacology appearing over 4,000 years ago. But medicine tablets, like the Nippur Pharmacopoeia, are just one category in a broader corpus of medical texts scattered across Mesopotamian history. Other tablets describe surgical procedures in equally specific detail. One text from the 1st millennium BC, copying earlier Sumerian material, describes treatment for cranial injuries. If a man suffers a head wound and the bone is shattered, you shall open the wound, remove the fragments, clean thoroughly with beer and wine, and close the opening. This is trepanation, deliberate surgical opening of the skull, described matter-of-factly in procedural language. Archaeological evidence confirms the practice. Skulls excavated from Mesopotamian sites show circular cranial openings with clear evidence of bone healing, indicating patients survived the procedure. Trepanation is among the most dangerous surgeries possible with ancient technology. It requires understanding skull anatomy, managing bleeding, preventing infection, and closing the wound in ways that allow healing. The fact that Mesopotamian physicians performed it successfully enough to leave healed skulls in the archaeological record indicates considerable surgical skill. Other tablets describe eye surgery. One text details a procedure for treating cataracts. If a man's eye is covered with a membrane, you shall take a bronze lancet, pierce the membrane, draw the water from the eye, and apply healing ointments. This describes couching, a surgical technique for treating cataracts by dislodging the clouded lens. It requires precision instrumentation, steady hands, and knowledge of eye anatomy. The procedure was practiced in ancient India and Greece as well, but the Mesopotamian descriptions are among the earliest, suggesting independent development or shared knowledge from an older source. The surgical texts reference specialized instruments, bronze lancets, copper hooks, obsidian blades, and various implements whose exact function remains unclear because the Sumerian terms no longer have certain translations. But tool inventories from temple complexes list surgical equipment among medical supplies, confirming that physicians possessed dedicated instruments for specific procedures. Texts also describe wound treatment following a systematic protocol. For open wounds, cleansing with water, beer or wine, all of which have antiseptic properties, though the texts don't use that terminology. Then, application of mixtures containing honey, plant resins or specific powders. Modern analysis of these ingredients reveals them to be genuinely medicinal. Honey is antibacterial. Certain plant resins have antimicrobial properties. The Mesopotamian physicians were using effective treatments, not merely symbolic ones. For fractures, the texts describe setting broken bones, applying splints, and using bandages, standard orthopedic practice that hasn't changed in principle for millennia. One tablet specifies treatment for a broken collarbone. You shall bind the arm tightly to the side, apply padding, and leave the binding in place for 30 days. This is mechanically correct. Restricting motion allows healing. The time frame is reasonable. The procedure works. Mesopotamian medicine distinguished between two types of practitioners: the Az, a physician who treated illness with physical interventions, and the Ipu, a priest-exorcist who addressed spiritual causes. But these roles weren't rigidly separated. Many texts show them working together, with the As providing medical treatment while the Ipu performed rituals. This suggests a sophisticated understanding that healing involved both physical and psychological dimensions, what we'd now call holistic medicine. The medical texts also categorize diseases systematically. They describe symptoms with clinical precision. If a man's urine is red and burns him when he passes it, or if a man's skin becomes yellow and his eyes likewise, these are recognizable descriptions of hematuria and jaundice. The physicians were observing patients carefully, noting symptoms, and correlating them with diagnoses. Some texts include prognoses. If these symptoms are present, the patient will recover. If those symptoms develop, he will not survive. This implies tracking of outcomes, knowing which combinations of symptoms predicted death or recovery based on observed patterns across multiple cases. That's evidence-based medicine, learning from experience and recording the lessons for future practitioners. What's particularly striking is the sophistication appearing so early. The Nippur Pharmacopoeia from 2600 BC isn't primitive, it's already systematic. The surgical texts describe complex procedures without explaining basics, as if writing for practitioners who already possess fundamental knowledge. Where did they learn it? Medical knowledge requires institutional structures. You can't train surgeons without supervision. You can't teach anatomy without dissection or extensive observation. You can't develop pharmacology without systematic experimentation, tracking which treatments help, which harm, and which do nothing. All of this requires time, resources, and social support for specialized learning. The Mesopotamians had medical schools. We know this because some tablets are clearly teaching materials, student copies of standard texts, sometimes with errors corrected by instructors. Temple complexes housed healing shrines where patients received treatment and where, presumably, trainees observed experienced physicians. This represents institutional medicine, not individual healers working in isolation. But the institutions themselves appear suddenly in the archaeological record. The earliest medical tablets don't show preliminary stages of medical knowledge development. They show functioning healthcare systems already in place, training practitioners in established procedures. It's as if Sumerian medicine began at an advanced level rather than building up from simple beginnings. Where did the anatomical knowledge come from? The texts describe internal organs with accuracy that suggests direct observation. They distinguish between arteries and veins. They understand that pulse correlates with heart function. They recognize that certain head injuries cause paralysis on the opposite side of the body. Knowledge that requires understanding the brain controls the body and that nerve pathways cross. How did they learn this? Ancient Near Eastern cultures generally prohibited human dissection for religious reasons. Animals could be examined, and extensive veterinary texts show Mesopotamian physicians understood animal anatomy well. But the medical texts describe human-specific conditions with detail that seems to exceed what could be learned from animal analogy or external observation of injuries. Either they found ways to study human anatomy despite religious prohibitions, or they inherited anatomical knowledge from predecessors who had. Some tablets include illustrations, drawings of organs, body parts, or medical instruments. These are schematic rather than realistic, but they convey information efficiently. One tablet shows a diagram of the liver divided into sections, each labelled with divinatory significance. The liver model indicates the physicians understood its internal structure with enough precision to segment it systematically. Most mysteriously, some medical texts describe treatments that wouldn't reappear in Western medicine for millennia. The use of mouldy bread on wounds, a practice that seems irrational until you realise mould produces natural antibiotics, the principle behind penicillin. The texts don't explain why mouldy bread helps, they just note that it does. Similarly, they describe using willow bark for pain. Willow contains salicylic acid, the active ingredient in aspirin. Did they understand the chemistry? No, but they had identified effective treatments through processes that must have involved careful observation and retention of successful procedures across generations. By the first millennium BC, some of this medical knowledge was eroding. Later tablets copying older medical texts include notes like "this plant is no longer identified," or "this procedure is from ancient times and is not practiced now." Certain surgical techniques vanish from the record. Recipes for specific medicines disappear. The continuity of medical knowledge, like mathematical knowledge, suffered interruptions. This erosion matters because medical knowledge is costly to develop. Each treatment represents trial across many patients. Each procedure refined through experience with successes and failures. Each recipe tested and adjusted. That investment vanishes when transmission breaks. Later physicians starting over must rediscover everything at tremendous human cost. The Mesopotamian medical tablets document a corpus of knowledge that took centuries to develop, longer than recorded Mesopotamian history itself. They describe physicians who performed brain surgery, cataract operations, and complex pharmacological treatments with enough success that their methods were considered worth preserving in institutional teaching texts. These practitioners shouldn't exist in 2600 BC according to conventional narratives of medical history. Yet the tablets prove they did, and those same tablets hint that what we're seeing is already a reduced version of earlier knowledge. The Sumerian physicians were preserving what they knew, copying older texts, transmitting procedures they'd inherited. But from whom? Where's the earlier civilization that developed this medicine? Or were the Sumerians themselves, the original developers, achieving in a few centuries what conventional historical thinking suggests should require millennia? The tablets don't answer. They only record, here's how to treat this condition, here are the ingredients for this medicine, here's the procedure for this surgery. Instructions without origin stories. Knowledge presented as eternal rather than invented, as if the question of where it came from never occurred to the scribes who copied these texts, because to them this wisdom had simply always existed, passed down from teachers who learnt it from earlier teachers in chains of transmission stretching back to beginnings no one remembered or needed. To explain, metals from fire. Copper doesn't announce itself. In its natural state, oxidized and weathered, it appears as green or blue stains on rock, malachite and azurite, minerals that ancient peoples initially used as pigments and decorative stones. Someone, at some point, had to make the cognitive leap from coloured stone to extracting metal. This requires recognizing that beneath the surface appearance lies a different substance entirely, one that can be liberated through heat. The earliest evidence of copper smelting in Mesopotamia dates to around 5000 BC, appearing at sites in northern Iraq and eastern Turkey. These early operations were small scale, using simple furnaces that reached temperatures around 1100 C, just hot enough to reduce copper ore to metal. The process produces pure copper, soft and malleable, useful for decorative objects and simple tools, but too weak for serious applications. By 3000 BC, Sumerian metalworkers were producing bronze, copper alloyed with tin. This wasn't an obvious progression. Tin and copper ores don't occur together naturally in Mesopotamia. Tin had to be imported from distant sources, possibly Afghanistan or Anatolia, requiring trade networks spanning hundreds of miles. Someone had to discover that adding roughly 10% tin to molten copper produced an alloy superior to either metal alone, harder, more durable, and better for casting. Bronze metallurgy represents a remarkable technical achievement. The melting point of copper is 1085 C, while tin melts at only 232 C. Working with both requires furnace technology capable of precise temperature control. Too cool and the metals won't melt, too hot and oxidation ruins the product. The right temperature must be maintained long enough to thoroughly mix the molten metals into a homogeneous alloy. Mesopotamian tablets from the 3rd millennium BC describe bronze production with procedural specificity, suggesting systematic understanding. One text from Ur lists copper and tin quantities in exact ratios, 4 bronze vessels, 90 parts copper, 10 parts tin. Another describes crucible preparation, flux additions to prevent oxidation, and cooling procedures. These aren't experimental notes. They're standard operating procedures, written for craftsmen who already know the basics. The tablets also reference quality control. Finished bronze could be tested by striking it, good bronze rings clearly, while impure metal thuds. Texts describe colour inspection. Proper bronze has a golden hue, while over-oxidized metal looks dull. These quality markers indicate metalworkers understood that invisible factors, oxide content, alloy homogeneity, crystal structure, affected visible properties and performance. Archaeological excavations of metalworking sites reveal sophisticated facilities. At Ur, archaeologists found workshop complexes with multiple furnaces, crucibles, moulds and storage areas for raw materials and finished goods. The layout suggests organised production with specialised workers, some managing fires, others pouring metal, still others finishing castings. This was industrial scale manufacturing, not individual artisans working alone. The Sumerians also produced arsenical bronze, copper alloyed with arsenic rather than tin. Arsenic bronze is harder than pure copper and easier to cast than tin bronze, but arsenic is toxic. Prolonged exposure causes neurological damage, skin lesions, and respiratory problems. Metalworkers using arsenical bronze would have suffered health consequences, yet they continued the practice for centuries. Why? Perhaps because arsenic copper occurs more naturally. Some copper ores contain arsenic as an impurity, producing the alloy automatically when smelted. Or perhaps because they understood the trade-off, better material properties in exchange for occupational hazards. Either way, it suggests metalworkers made informed choices about which alloys to produce for which applications. Tablets from later periods also describe ironworking, though this came later to Mesopotamia than bronze. Iron smelting requires higher temperatures, around 1500 C, and produces a spongy mass of iron mixed with slag that must be hammered repeatedly to consolidate. The process, called bloomery iron production, is labour-intensive and technically demanding. Early iron was actually inferior to good bronze. It corroded more easily and wasn't inherently harder. What made iron valuable was abundance. Iron ore is far more common than copper or tin, and the discovery that iron could be carburized. By heating iron in contact with charcoal and then rapidly cooling it, smiths could produce steel harder than any bronze. But this carbonization process isn't intuitive. Someone had to discover that introducing carbon transformed iron's properties, then develop techniques to control the process. Mesopotamian tablets from the 1st millennium BC reference iron tools and weapons using terminology that distinguishes different types: good iron, black iron, strong iron. These terms likely refer to different carbon contents, wrought iron versus steel. The vocabulary indicates smiths recognized variations in iron quality and probably controlled production to achieve desired properties. What's notable across all this metallurgical development is the absence of visible trial and error. We don't find archaeological sites littered with failed experiments. We don't have tablets describing mishaps or recording dead ends. What we find is competent production appearing relatively suddenly, already optimized, with quality standards and specialized facilities. Consider what developing bronze metallurgy from scratch would require. You'd need to identify that certain rocks contain extractable metal, develop furnaces capable of reaching 1100 C+, recognize that mixing copper with other metals might improve it, source tin from distant regions, experiment with different ratios, to find optimal alloy proportions, develop crucibles that withstand repeated heating, create moulds for casting complex shapes, discover techniques for finishing and strengthening the metal, establish quality standards and testing procedures, train specialists and organise production facilities. Each step requires investment and expertise. Many attempts would fail. Much material would be wasted. Yet by the time this appears in the Sumerian archaeological record, it's already functioning efficiently. The early bronze artefacts show skilled workmanship. The production sites show organised industry. The tablets describe procedures as routine rather than experimental. Where did this knowledge come from? The conventional answer is that it developed gradually across centuries, with each generation adding refinements. But the archaeological evidence for those centuries of development is sparse. We see simple copper working around 5000 BC, then sophisticated bronze production by 3000 BC. 2000 years sounds like plenty of time, but it's not if you're starting from zero with no guidance. Compare this to later historical developments. When Europeans learned bronze metallurgy, they had Middle Eastern examples to study and teachers who could explain principles. When Chinese smiths developed their distinctive bronze techniques, they built on existing metalworking traditions. Knowledge transmission accelerated the process. But who taught the first Mesopotamian metalworkers? The Sumerians' own texts don't claim to have invented metallurgy. They attribute it to the gods, specifically to Enki, who gifted humanity the knowledge of working copper and tin. Is this merely mythology, or does it preserve a memory of knowledge transmission from an earlier source? Some tablets contain phrases like the old method of the forge, or according to ancient practice. These references appear in texts from the 2nd and 1st millennia BC, looking back to earlier periods. They suggest the scribes themselves viewed their metallurgical knowledge as inherited rather than contemporary invention, and some of that knowledge was forgotten. Certain copper alloys described in 3rd millennium tablets don't appear in later periods. Specific surface treatments mentioned in early dynastic texts are absent from Neo-Assyrian records. The knowledge base contracted. Later metalworkers possessed less understanding than their predecessors, not more. This pattern, sophisticated knowledge appearing early, then partially eroding, contradicts the expected trajectory of technological progress. It suggests fragility in knowledge transmission. When the institutions supporting specialized knowledge collapsed during periods of warfare or economic crisis, expertise vanished. Later civilizations in the same region had to work from incomplete records, tablets describing procedures they couldn't fully replicate. The bronze artifacts preserved in museums represent frozen moments of applied knowledge. Each one required a smith who understood temperatures, alloy ratios, mould preparation, and finishing techniques. Behind each finished piece stands accumulated expertise, someone who knew how to make bronze well enough to produce objects that lasted 4,000 years. But the path to that expertise remains obscure. The tablets record the results, mix copper and tin in these proportions, without explaining how anyone discovered those proportions in the first place. They preserve procedures without documenting the learning process that generated them. It's as if the authors assumed readers already understood the underlying principles and only needed procedural reminders. Or perhaps they were themselves copying instructions they'd inherited, maintaining procedures their teachers had taught them, preserving knowledge whose origins had been forgotten generations earlier. The metalworkers of Ur-Lagash may have been practitioners of techniques that predated written records, techniques that had been refined over centuries before anyone thought to write them down. The furnaces went cold thousands of years ago, the workshops crumbled, the smiths died and their knowledge died with them, or would have, except that some of them pressed styluses into clay tablets, recording procedures so that future metalworkers could continue the craft. Those tablets survived fires, floods, and millennia of burial to reach museum collections where scholars could read them again. But reading them isn't the same as understanding them. We can translate the words, we can replicate some procedures, but we've lost the embodied knowledge, the smith's feel for when metal reaches the right temperature, the practiced eye that judges alloy quality from colour, the accumulated wisdom of hundreds of small adjustments that separate competent work from mastery. That knowledge died with the last practitioners. The tablets couldn't capture it. And so another piece of what the ancient world knew slipped away, leaving only fragmentary descriptions and the finished objects themselves, silent testament to capabilities we can admire but not fully recover. The astronomers of Uruk. The night sky over Mesopotamia is brilliant in ways modern urban dwellers rarely experience. With no light pollution, stars fill the darkness from horizon to horizon, thousands visible to the naked eye, their positions and movements marking the passage of time with predictable regularity. Ancient observers learned this sky intimately, not as aesthetic wonder, but as essential calendar and clock. Agricultural civilizations require precise calendars, knowing when to plant, when floods would come, when seasons would turn, meant survival. The sky provided the only reliable timekeeping mechanism available. The sun's daily arc, the moon's monthly phases, the seasonal appearance and disappearance of particular stars. These patterns governed human activity. But Mesopotamian astronomy went far beyond practical calendar keeping. By the 2nd millennium BC, Babylonian astronomers were tracking planetary motions, predicting eclipses, and recording observations with precision that seems excessive for mere agricultural timing. They were studying the sky systematically, accumulating data across generations, searching for patterns. The great astronomical compendium called Enuma Anu Enlil, when the gods Anu and Enlil comprised 70 or more tablets covering celestial omens. These weren't random superstitions. They were systematic correlations between celestial events and terrestrial outcomes, recorded over centuries of observation. The series represented institutional knowledge maintained by scribal communities who copied and updated the tablets across generations. Individual tablets within Enuma Anu Enlil focus on specific phenomena. Some track lunar eclipses, documenting the dates, durations and visibility conditions of every eclipse observed across centuries. Others follow planetary movements. Venus tablets record its appearances and disappearances over multi-year cycles. Still others track stars, noting heliacal risings and settings throughout the year. The precision is striking. One tablet, referenced in the British Museum's collection as K4292, preserves eclipse predictions using geometric calculations. The astronomers understood that eclipses followed patterns, the Saros cycle, an 18-year-plus period after which eclipse sequences repeat. Recognizing this pattern requires data spanning multiple cycles, meaning observations accumulated over decades at minimum. But the tablets reference even longer observation periods, some site data from the time of the ancestors or ancient observations. These phrases appear in first millennium texts discussing celestial events from earlier periods. The astronomers were working with inherited datasets, building on centuries of accumulated records. Consider what maintaining such records required. Each night, observers had to note celestial positions, not casually, but precisely enough to detect changes. They needed reference systems, ways of describing where objects appeared relative to fixed stars or horizon positions. They needed standardized notation so observations made by different people at different times could be compared. They needed institutional support, temple or palace backing that provided resources for observers who produced no immediate practical benefit. And they needed confidence that the work mattered, that patterns existed worth finding. This is perhaps the most remarkable aspect, the faith that systematic observation would eventually reveal celestial order. Many ancient peoples watched the sky. The Mesopotamians turned watching into systematic science. The Venus tablets of Amisaduqa, recording appearances and disappearances of Venus during the reign of the Babylonian king Amisaduqa around 1650 BC, demonstrate this systematic approach. Venus as an inner planet displays complex motion from Earth's perspective, sometimes appearing as morning star, sometimes as evening star, sometimes invisible for weeks. The tablets track these appearances with dates recorded in the Babylonian calendar, noting positions and duration of visibility. Scholars analysing these tablets have used them to investigate ancient chronology, working backward from the Venus data to constrain possible dates for Amisaduqa's reign. The fact that this is possible, that the observations were precise enough to survive 3,600 years and still be astronomically useful, speaks to the observer's care and accuracy. The Babylonians also tracked Jupiter, Mars, Saturn and Mercury, each requiring different observation strategies. Jupiter's motion through the zodiac takes 12 years. Saturn takes nearly 30. Recognizing patterns in their movements requires multi-generational datasets. No single astronomer could observe enough to identify the cycles. Knowledge had to accumulate across lifetimes. By the first millennium BC, Babylonian astronomers were making predictions. Mathematical astronomical texts from this period used computational methods to calculate future planetary positions without direct observation. They'd identified numerical patterns in the planet's complex motions and developed algorithms to project those patterns forward. These methods involved what modern scholars call zigzag functions, piecewise linear approximations that model celestial motion using arithmetic sequences. It's not calculus, but it's sophisticated computational astronomy using geometry and arithmetic to predict change over time. Scholars debate whether this represents the earliest known form of predictive scientific modelling. But here's the mystery. The computational methods appearing in first millennium tablets seem more advanced than earlier astronomical work, yet the precision of predictions declined. Earlier observations were more accurate than later computational results. This suggests the algorithms were approximations of better methods that had been lost, simplified versions that preserved prediction capability but sacrificed accuracy. Why simplify? Perhaps because the original methods required understanding that later astronomers no longer possessed. Perhaps the computations were shortcuts, ways to generate predictions without fully grasping the underlying geometry. The tablets preserve the algorithms, but not always the reasoning behind them. Some texts include commentary noting difficulties. One scribe, copying an astronomical tablet, added a note: "The calculation method in this section is unclear to me. I have copied it as written, but cannot verify its correctness." The scribe recognized his own limited understanding, preserving the text faithfully despite not comprehending it fully. This pattern recurs across Mesopotamian astronomy, later periods working with knowledge inherited from earlier ones, maintaining traditions they incompletely understood. The institutional structures supporting astronomy weakened over time. Wars disrupted observations. Economic pressures reduced temple support for scholarly activities. The chain of transmission frayed. Yet even in decay, Babylonian astronomy remained impressive. When Greek astronomers encountered Mesopotamian astronomical knowledge in the Hellenistic period, they were stunned by the depth of the observational datasets. Ptolemy, writing his Almagest in the 2nd century AD, relied heavily on Babylonian observations, citing data points from centuries earlier preserved in cuneiform tablets. The Greeks built theoretical models, geometric systems of circles and epicycles explaining planetary motion. The Babylonians had developed computational methods without equivalent theoretical frameworks, or at least without ones preserved in surviving tablets. They could predict where planets would be without necessarily explaining why. This suggests either that Babylonian astronomy was purely empirical, pattern finding without theory, or that theoretical understanding existed but wasn't written down, transmitted orally within astronomical communities. If the latter, then what survives in tablets represents only part of Babylonian astronomical knowledge. The written records were reference materials, computational aids, data archives. The deeper understanding, the why behind the predictions, lived in trained minds. When those communities dissolved, that understanding vanished, leaving only the computational recipes and observational data. But even that reduced corpus influenced later civilizations profoundly. Islamic astronomers in medieval Baghdad rediscovered cuneiform tablets and learned from Babylonian methods. Renaissance European astronomy built on Greek traditions that had themselves absorbed Babylonian datasets. The chain of knowledge stretched across millennia, each civilization adding to and modifying what came before. What we see in the astronomical tablets, then, is knowledge in transit, moving from earlier observers to later computers, from Babylonians to Greeks to Arabs to Europeans. At each transfer, something was lost and something added. The original observations made by patient Mesopotamian astronomers watching the night sky from temple rooftops became data points in increasingly sophisticated mathematical models, their origin forgotten, their context erased, until only numbers remained, divorced from the human effort that generated them. And somewhere in that long transmission, the question of origin became obscured. By the time Greek astronomers encountered Babylonian astronomy, they treated it as ancient wisdom without asking how it began. They inherited datasets spanning centuries without questioning who started compiling them or why. The tablets themselves don't explain. They simply present observations and calculations as if the practice of systematic astronomy were eternal, requiring no justification or origin story. But it did have an origin. Someone at some point decided that tracking celestial movements mattered enough to invest resources in systematic observation. Someone organized the first observers and created the first recording systems. Someone taught the first students how to measure star positions and note them in cuneiform. That beginning is lost to us, buried deeper than any excavated tablet, existing only as inference from what came after. Glass, beer, and forgotten chemistry. Glass is frozen liquid, a substance caught between states. At high temperatures, silica flows. Cooled quickly, it retains liquid structure even while solid, molecules arranged in disordered patterns rather than crystalline precision. This makes glass transparent, fragile, and strangely timeless. Ancient glass artifacts have survived millennia, their surfaces weathered, but their forms intact. The Mesopotamians didn't invent glass. The oldest known glass objects come from Egypt around 3500 BC, but they refined its production. By the second millennium BC, Mesopotamian workshops were producing glass vessels, beads, and inlays with sophisticated techniques, and they wrote down their methods. A collection of tablets from the Middle Assyrian period, circa 1200 BC, preserves glass-making recipes with remarkable specificity. These aren't brief notes. They're detailed procedural texts describing material preparation, furnace operation, colour additives, and finishing techniques. One tablet begins: for making zoot glass, take 60 parts clean sand, take 180 parts ash of glasswort, combine in the furnace, heat until the mixture flows like water. The recipe specifies proportions precisely: 3,001 ash to sand by weight. It identifies particular materials: glasswort, a salt-tolerant plant whose ashes provide sodium carbonate, the flux that lowers silica's melting point from 1700 C to more manageable temperatures around 1100 C. The text understands that not just any plant ash works, glasswort specifically, whose high alkali content makes it effective. Other tablets describe colour additions: For green glass, add 90 parts copper filings. For blue, add copper and lapis lazuli powder in equal measure. For white, add tin oxide, 20 parts. Each colorant requires different handling. Some must be added during initial melting, others during reheating. The tablets specify these sequences, indicating glassmakers understood that timing affected results. The procedural language is precise. Heat until you see the mixture bubble and clear. Do not remove from fire too early, or the glass will be cloudy and weak. When the surface becomes still and smooth, the glass is ready. This describes the process of fining, allowing bubbles to rise and escape, which requires maintaining temperature long enough for viscous glass to release trapped air. Modern glassmakers recognize this as essential to producing clear, strong glass. What's striking is the sophistication implied. These aren't accidental discoveries. Glassmaking requires understanding relationships between silica, fluxes, stabilizers and colorants. It requires controlled high-temperature furnace operation. It requires knowledge of how to manipulate viscous materials, shaping them before they cool and harden. This represents chemical engineering, empirical but systematic. How did the Mesopotamians develop this knowledge? The tablets don't say. They present recipes as established procedures, written for practitioners who already understand basics. There's no explanation of why these proportions work, no discussion of unsuccessful experiments, no narrative of discovery, just instructions: do this, add that, heat to this point, and you'll produce glass. The tablets also note that these are copies of older texts. Colophons mention according to ancient formula or from the time of earlier craftsmen. The Middle Assyrian scribes were preserving knowledge inherited from earlier glassmakers, recording techniques they practiced but hadn't invented. This pushes origins back further into periods less documented, where the original discovery process is completely obscured. Beer-making tablets show similar patterns. Brewing beer was essential in Mesopotamia, water quality was unreliable, but fermented beverages were safer and nutritionally valuable. The process appears in texts as early as 3500 BC, and by 1800 BC we have the famous hymn to Ninkasi, which doubles as both religious poetry and brewing recipe. The hymn praises Ninkasi, the Sumerian goddess of brewing, while describing beer production step by step. You are the one who handles the dough with a big shovel, mixing in a pit of beer with sweet aromatics. You are the one who bakes the beer in the big oven, puts in order the piles of whole grain. You are the one who waters the malt set on the ground. Decoded from poetic language, this describes malting, soaking barley until it germinates, then drying it to develop enzymes that convert starches to sugars. The bapir was a twice-baked barley bread, partially fermented before baking, which provided yeast and flavour to the beer. The process then involves soaking this bread with malted grain in water, allowing fermentation and straining the result. This is sophisticated brewing. Malting requires understanding that germination activates enzymes. Using bapir as yeast source requires recognizing that fermentation can be controlled by inoculation. The proportions matter. Too much grain makes thick beer, too little makes weak beer. Temperatures during fermentation affect flavor. Ancient brewers controlled all these variables, producing different beer styles for different purposes. Tablets from administrative archives track beer production at industrial scales. Temple complexes brewed thousands of litres monthly, distributing it as worker rations. Texts specify different beer types: black beer, red beer, sweet beer, strong beer. Each required different recipes and techniques. This represents not just brewing capability, but quality control and product differentiation, managing production to achieve consistent, desired characteristics. The chemistry involved is non-trivial. Fermentation converts sugars to alcohol through yeast action. Mesopotamian brewers didn't understand microbiology, that came 4,000 years later, but they understood that something in the fermentation process produced alcohol. They knew how to maintain that process, how to recognize when fermentation completed, how to stop it at the right point. They also knew preservation techniques. Beer doesn't last indefinitely, it spoils, but certain brewing methods extended shelf life. Higher alcohol content inhibited bacteria. Boiling the wort killed contaminants. Proper storage in sealed vessels prevented spoilage. The tablets don't explicitly discuss these principles, but the procedures they describe incorporate them, suggesting practical knowledge even without theoretical understanding. This pattern, sophisticated practice without stated theory, appears throughout Mesopotamian chemical knowledge. They could smelt metals, make glass, brew beer, produce dyes, prepare medicines, and manufacture building materials, all requiring understanding of chemical transformations. Yet tablets describe procedures without explaining mechanisms. They tell you what to do, not why it works. Does this mean they didn't understand why, or that they simply didn't write down theoretical explanations? In oral teaching environments, procedures might be demonstrated while principles are explained verbally. Students would learn both what and why, but only the procedural what gets recorded in tablets as reference material. If so, then the tablets represent only part of Mesopotamian chemical knowledge. The deeper understanding lived in communities of practitioners, transmitted through apprenticeship and observation. When those communities dissolved, theoretical knowledge vanished, even as written procedures survived. Later texts show this erosion. First millennium tablets copying older glass recipes include notes like "this ingredient is no longer available" or "modern craftsmen do not produce glass of this quality." The procedures survived, but materials changed or techniques were lost. Later glassmakers had instructions they couldn't fully execute, recipes calling for materials they couldn't obtain, or processes they didn't completely master. The same happened with beer. By the first millennium BC, some beer styles mentioned in earlier texts had disappeared. Certain brewing techniques were no longer practiced. The art contracted, simplified, as knowledge transmission weakened. Yet even in simplified form, Mesopotamian brewing influenced later civilizations. Egyptian brewing shared techniques with Mesopotamian methods, suggesting knowledge exchange. Medieval European brewing incorporated principles that traced back through complex pathways to ancient Near Eastern practices. The knowledge persisted, transformed, fragmentary, but continuous. What the glass and beer tablets reveal is practical chemistry developed to high sophistication without modern theoretical frameworks. The Mesopotamians couldn't explain molecular structures or chemical reactions, but they could manipulate them skillfully. They learned through observation and experiment, refined techniques across generations, and recorded what worked. But they also recorded losses, knowledge that once existed but had faded, and they recorded their awareness of inheriting rather than inventing, copying ancient formulas whose origins they didn't claim to know. Somewhere behind these Middle Assyrian glass recipes and Old Babylonian brewing hymns lay earlier chemists, original experimenters, knowledge creators whose names and stories weren't preserved. The glass and beer survived. The tablets describing their production survived. But the people who first figured out that sand and ash could be melted into transparency, that grain and water could be transformed into intoxication, those people vanished into prehistory, leaving only their recipes behind, instructions floating free of inventors, techniques divorced from discoverers, as if the knowledge itself were more durable than the minds that generated it. The technologies that vanished. Sometimes what isn't in the tablets matters as much as what is. Historians of technology speak of technological regression, the loss of capabilities that earlier periods possessed. This isn't supposed to happen. Technology, according to progressive models of civilization, should accumulate. Each generation builds on its predecessors, adding innovations while retaining existing capabilities. Knowledge should grow. But Mesopotamian history shows something different. Capabilities documented in 3rd millennium tablets disappear from 2nd millennium records. Techniques described confidently in early dynastic texts are absent from later periods. Materials produced routinely in earlier eras become rare or vanish entirely. The archaeological and textual evidence documents not just gains but losses, not just accumulation but erosion. Consider certain glass formulations. 3rd millennium tablets describe glasses with properties that later texts don't match. Modern analysis of glass artifacts from different periods shows compositional changes. Earlier glass contains elements not present in later examples. Specific colorants disappear. Certain optical qualities aren't replicated in later work. This isn't because later glassmakers lacked materials. The raw ingredients remained available. What changed was knowledge. The recipes for particular glasses weren't transmitted successfully, or the techniques for achieving specific results were lost. Later craftsmen worked with incomplete instructions, producing glass, but not the full range their predecessors had achieved. Medical tablets show similar losses. Certain surgical procedures described in 3rd millennium texts aren't mentioned in later periods. Specific pharmaceuticals vanish from later recipes. The Nippur Pharmacopoeia from 2600 BC lists treatments not found in 1st millennium medical texts. Either medicine regressed, practitioners forgot procedures, or practices changed for reasons not recorded in surviving tablets. Some losses are explicitly documented. A 1st millennium tablet copying an older architectural text includes a note: the mortar formula described here is no longer known. Modern builders use different methods. The scribe acknowledged that construction techniques had changed, with earlier methods abandoned or forgotten. Why does this happen? In some cases, external disruptions explain it. Wars destroyed cities, killing craftsmen and burning libraries. The Gutian invasion around 2150 BC devastated Sumerian civilization, ending the Ur III period. Many texts weren't copied, many techniques weren't transmitted. When civilization recovered, some knowledge had been lost. Economic collapse produced similar effects. Maintaining specialized knowledge requires resources, schools, libraries, patronage for practitioners whose work doesn't immediately generate profit. When economies contracted, specialized learning became unaffordable luxury. Fewer students trained in advanced techniques. Fewer texts were copied and preserved. The knowledge base narrowed to essential practical skills. Political fragmentation also disrupted transmission. In unified empires, knowledge circulated widely. When empires collapsed into competing city-states, information flow restricted. Techniques known in one region didn't reach others. Centres of expertise fell, and their knowledge died with them. But some losses seem independent of catastrophe. They occurred during stable, prosperous periods when institutional support existed. These suggest different causes, perhaps changes in materials or demand. If tin supplies became unreliable, bronze-making techniques specific to tin bronze would fade as smiths switched to alternative alloys. If certain medicinal plants became scarce, recipes using them would be abandoned for substitutes. Or perhaps some knowledge was deliberately restricted. Secret formulas, known only to particular families or guilds, would vanish if those groups died out or stopped teaching. Temple techniques, restricted to priestly communities, could be lost if temples closed, or religious practices changed. Deliberate secrecy, protective of specialized knowledge, ironically makes that knowledge more vulnerable to loss. The cuneiform record hints at this. Some tablets are marked secret or not to be shown to the uninitiated. Medical texts sometimes end with injunctions. Let the wise explain to the wise. The ignorant should not see this. These restrictions suggest knowledge hierarchies with advanced information controlled by elites. But elite-controlled knowledge is fragile. It depends on continuous transmission within small communities. Break that chain, and the knowledge vanishes entirely. One particularly striking example involves architectural techniques. Some 3rd millennium Sumerian buildings display construction sophistication not seen in later structures. The precise cutting of large stones, the methods for lifting and placing heavy blocks, certain joining techniques, these appear in early dynastic architecture but are absent or cruder in later periods. Did they forget how to build as well? Or did they simply stop doing it, perhaps because labour costs increased or architectural fashions changed? It's difficult to determine whether absence reflects knowledge loss or choice, but the result is the same. Capabilities demonstrated in earlier periods don't appear in later ones. The same pattern appears in textile production. Some early dynastic texts describe weaving techniques producing fabrics whose construction isn't clear from later texts. Either the techniques changed, or the vocabulary shifted such that later scribes used different terms for the same methods, creating apparent discontinuity where none existed. Disentangling real knowledge loss from documentary changes challenges historians, but certain losses are undeniable. By the 1st millennium BC, Mesopotamian civilization preserved texts they couldn't fully understand. Medical tablets contain plant names no longer identified. Mathematical texts described procedures whose purposes weren't clear. Astronomical observations from earlier periods were copied without comprehension of the significance. The scribes preserved these texts because they recognized them as important, even when meaning had been lost. This is poignant, the act of conservation without comprehension, maintaining documents in hope that future generations might recover what the present could no longer grasp. What this reveals is knowledge as fragile. Civilization's achievements, its accumulated understanding, depends on continuous active transmission. Each generation must teach the next, not just handing over tablets, but explaining them, demonstrating techniques, passing on embodied skills that texts can't fully capture. When that transmission breaks, through catastrophe, economic stress, or simple neglect, knowledge evaporates with shocking speed. Within a generation, sophisticated techniques become dimly remembered. Within 2, they're lost entirely. The tablets remain, words still legible, but meaning gone. Later civilizations inherit the record, but not the understanding, leaving them to puzzle over instructions they can read, but not comprehend, recipes they can follow, but not reproduce, references to capabilities their ancestors possessed, but they themselves have lost. And sometimes those later civilizations don't even recognize what's missing. They assume their capabilities match or exceed their predecessors. Only when scholars compare early and late periods does the regression become visible. Earlier peoples knew things, did things, made things that later peoples couldn't match. This challenges progressive narratives of history. It suggests that civilization doesn't inevitably advance, that knowledge can be lost as easily as gained, that what we inherit from the past may be less complete than what our ancestors possessed. The Mesopotamian tablets document this loss, recording both achievement and its disappearance, preserving descriptions of capabilities that vanished, leaving only the descriptions themselves as testimony that once, somewhere in the deep past, people knew how to do things we've since forgotten. Electricity before wire. In 1936, German archaeologist Wilhelm Knig was cataloguing artifacts at the National Museum of Iraq in Baghdad when he noticed something peculiar among items excavated from Qudrat Rabu, a Parthian site southeast of the city. The object consisted of a small clay jar about 14 centimetres tall with a copper cylinder inside. An iron rod ran through the cylinder, suspended by an asphalt plug that sealed the jar's mouth. The iron showed evidence of acid corrosion. Knig recognised a configuration that shouldn't exist in ancient Mesopotamia, the elements of a galvanic cell, a battery. The copper cylinder served as cathode, the iron rod as anode, and if the jar had been filled with acidic liquid vinegar perhaps, or wine, chemical reactions would have produced electrical current. Not much, perhaps a volt or two, but genuine electricity generated 2,000 years before Alessandro Volta's 1800 invention supposedly inaugurated the age of electrochemistry. The object became known as the Baghdad battery, though scholars debate whether it actually functioned as one. Alternative interpretations suggest it stored sacred scrolls or served as a ceremonial vessel. Experiments demonstrate it can generate current when filled with acidic solutions, but that doesn't prove ancient peoples used it for that purpose. Yet Nigg found multiple similar objects, suggesting not unique accident, but manufactured type. And the configuration is oddly specific. Why place an iron rod inside a copper cylinder, seal it with asphalt, and house it in a jar, unless that particular arrangement served a purpose? Accidental assemblage seems unlikely. Someone designed this structure intentionally. If these were batteries, what powered? Parthian civilization, circa 250 BC to 224 AD, left no records of electrical devices. No tablets describe electroplating or lighting or any application requiring electrical current. The objects themselves come from contexts suggesting religious or administrative use, not industrial manufacture. But absence of evidence isn't evidence of absence. Most ancient technologies left minimal archaeological traces. Wooden devices rotted, textile mechanisms disintegrated. Clay tablets recorded administrative records, not technical workshops. If Parthian craftsmen used electricity for specialized applications, perhaps electroplating gold onto silver or copper onto other metals, few traces would survive. Modern experimenters have demonstrated that Baghdad battery replicas can electroplate metal, immerse a silver object and copper electrode in electrolyte, apply current from a battery cell, and copper ions transfer to silver surface, creating a thin copper coating. The process works with technology available 2,000 years ago. Would ancient peoples have discovered this? Accidentally, perhaps. If you stored wine in a jar with copper and iron fittings, acidic wine would corrode metals, generating small current. If jewellery happened to be present, metal ions might deposit on it. An observant craftsman might notice metal colour changes and investigate systematically. Or the knowledge could have been transmitted, inherited from earlier traditions that understood electrochemical principles without modern theory. The Parthians occupied territories previously ruled by Babylonians, Assyrians and Persians, civilizations with sophisticated metallurgy spanning millennia. If any of those cultures discovered electrochemical effects, knowledge might have persisted through craft traditions, passed master to apprentice without written records. But here's what makes the Baghdad battery genuinely mysterious. Similar artifacts have been found at Seleucia, a city with Hellenistic roots, suggesting the technology wasn't unique to Parthia. If electrochemical cells were manufactured in multiple locations across centuries, they represented established technology, not isolated accident. The devices raise uncomfortable questions about ancient knowledge. Modern electrochemistry required understanding that chemical reactions could generate current, that different metals produce different voltages, that electrolytes facilitate ion transfer. These concepts weren't formalized until the 19th century. Yet if the Baghdad battery served electrical purposes, someone 2 millennia ago understood enough electrochemistry to design functional galvanic cells. Alternative explanations exist. Some scholars suggest the jars stored manuscripts, the copper cylinder protecting scrolls from moisture. Others propose magical or medicinal purposes. Perhaps the mild electric tingle had therapeutic applications, or priests used it for religious effects, creating divine sensations by conducting current through water participants touched. We can't definitively determine function from the artifacts alone. Without tablets describing their use, we're left with interpretations based on configuration and analogy. What we can say is this: Someone in Parthian Mesopotamia manufactured jars with copper cylinders, iron rods, and asphalt seals in numbers suggesting purposeful production. Whatever their function, it required that specific configuration, and that configuration generates electricity, a fact that remains true whether or not ancient peoples exploited it. The technology existed, materially present in archaeological strata from 2,000 years ago, challenging assumptions about when humans first harnessed electrochemistry. More broadly, the Baghdad battery symbolizes larger questions about ancient technological knowledge. How much did they understand that we assume they couldn't? How many capabilities did they possess that left minimal archaeological traces? How much knowledge was transmitted through practice rather than writing, existing as embodied skill rather than recorded theory? Cuneiform tablets record some technological knowledge, but mostly they document outcomes, finished products, completed projects, administrative resource allocation. The actual methods, the workshop practices, the craftsman's tricks, these weren't usually written. They were taught by demonstration, learned through apprenticeship, refined through practice. When those craft traditions broke, when workshops closed, when artisans died without apprentices, when economic collapse ended specialized production, the knowledge vanished. Later civilizations inherited artifacts, but not understanding. They found objects whose manufacture they couldn't explain, devices whose purpose they couldn't determine. The Baghdad battery may be exactly that, a remnant of technological knowledge whose context has been lost, leaving us with the physical artifact, but not the understanding that created it. We can analyze its structure, reproduce its function experimentally, speculate about its purpose, but we can't recover the knowledge that originally designed it, the reasoning that led some ancient craftsman to place iron inside copper, inside clay, to seal it with asphalt, to create a device whose function remains debated 2,000 years later. And if this one artifact generates such mystery, how many other ancient capabilities have vanished entirely, leaving no physical trace? How many technological achievements existed briefly, then disappeared before anyone thought to record them? The Baghdad battery survived by accident, durable materials, burial in dry soil, chance excavation. How many less durable devices simply dissolved back into soil, taking their secrets with them? The hydraulic engineers. Water defined Mesopotamian civilization. The region's name literally means between the rivers, the Tigris and Euphrates, that brought life to otherwise arid plains. But these rivers were dangerous benefactors. Unpredictable floods devastated fields. Irregular flow left canals dry. Managing water meant survival, and managing it well meant prosperity. By the 3rd millennium BC, Sumerians had transformed their landscape with hydraulic engineering at stunning scales. Canal networks stretched hundreds of kilometers, moving water from rivers to fields dozens of miles away. These weren't simple ditches. They were graded precisely to maintain steady flow. Too steep and water-eroded channels, too shallow and it stagnated. Ancient engineers achieved gradients measured in centimetres per kilometre across distances requiring surveying accuracy that seems improbable for their era. Excavations near Ur revealed canal systems dated to 3000 BC already sophisticated. Channels branch at carefully calculated angles. Control gates regulated flow. Reservoirs stored excess water for dry periods. The infrastructure demonstrates systematic planning. Someone designed these networks as integrated systems, not as isolated ditches dug as needed. How did they survey? Determining elevation changes across flat floodplains requires precision instruments. Modern surveyors use levels and theodolites. The Sumerians had neither, yet their canals maintained grades indicating elevation measurements accurate to small fractions of a metre across kilometres. Water level techniques could work. Fill a long trough with water, which naturally seeks level. Measure height at each end relative to ground. Move the trough and repeat. Tedious, but functional. Or use strings and plumb bobs, establishing level lines point by point. Again, tedious, but possible. What's remarkable isn't that they could do it, but that they did. That someone organised labour forces to dig canals with precise specifications across vast distances, convinced authorities to invest resources in projects whose benefits appeared only after completion, maintained institutional, memory long enough to complete works spanning years or decades. Tablets from the year 3 period, around 2100 BC, document canal maintenance, work crews assigned to clear silt, repair banks, dredge channels. These weren't improvised responses to failures. They were scheduled maintenance, systematic preservation of infrastructure. The texts reveal bureaucratic management of hydraulic systems, with officials responsible for specific canal segments, reports tracking condition, resources allocated for upkeep. This represents institutional sophistication matching technical achievement. Building canals requires engineering knowledge. Maintaining them requires administrative systems ensuring continuous care. Without maintenance, canals silt up within years. The Sumerian networks functioned for centuries, which means successful institutional management across generations. They also built water clocks, clepsydra, devices measuring time by water flow. These required precisely manufactured vessels. Water drains through a small opening at controlled rate. Markings on the interior show elapsed time as water level drops. Accuracy depends on consistent flow, which means the opening must be carefully sized and shaped. Mesopotamian water clocks appeared by the 2nd millennium BC, used in temples and courts to measure durations. Legal proceedings used them to allot time for arguments. Lawyers spoke until their allotted water ran out, a practice that gave rise to the phrase using up time. The devices had to be reliable enough for official use, which implies careful manufacture and calibration. Building water clocks requires understanding fluid dynamics, that flow rate depends on pressure, which depends on water height, so flow speeds up as the vessel drains. Simple clepsydrae show this effect, marking hours that grow shorter as time passes. More sophisticated designs compensate by shaping vessels, so decreasing pressure is offset by increasing area, maintaining constant flow rate. Did Mesopotamian water clocks incorporate such refinements? Some evidence suggests yes. Texts refer to clocks that measure equal hours, implying compensation mechanisms. But the devices themselves haven't survived. Made of clay or metal, they crumbled or were recycled long ago. Only the texts remain, describing devices we can't examine, referencing capabilities we must infer. The hydraulic engineering extended underground. Texts describe canat systems, underground channels tapping aquifers, moving water through subterranean tunnels to prevent evaporation. Building canats requires digging vertical shafts, then horizontal tunnels connecting them at precise depths and angles. This underground surveying is far more difficult than surface work, yet canats function only when properly aligned. Persian canat systems are well documented, some still functioning after 2,500 years. Their origins remain debated. Some scholars credit Persians with inventing the technology around 1000 BC. Others argue evidence points to earlier Mesopotamian development, with Persians adopting and refining existing techniques. The technology requires sophisticated understanding. You must locate aquifers, determine optimal tunnel depth, calculate gradients allowing water flow without erosion, and ventilate shafts adequately for workers. Each step demands expertise. The finished system functions invisibly, water flowing through darkness from source to destination, with no surface indication of the engineering making it possible. What we see in Mesopotamian hydraulics is comprehensive water management, canals, reservoirs, dikes, distribution networks, drainage systems engineered at civilization scale. This wasn't local irrigation expanded gradually. It was systematic transformation of landscape, planned and executed with technical sophistication that matches or exceeds what many later civilizations achieved. Yet the tablets describing these works are matter of fact. They record canal dimensions, labour assignments, maintenance schedules. They don't explain how engineers learned to design such systems, how surveyors achieved necessary precision, how planners organised multi-year projects requiring coordination of thousands of workers. The knowledge appears already mature in the earliest texts, suggesting development in earlier periods before writing. If so, Sumerian hydraulic engineering has origins in preliterate times, techniques refined over centuries of trial and refinement before anyone documented them in cuneiform. When those canal systems eventually failed, silted up during periods of weak maintenance, destroyed in wars, or abandoned as political centres shifted, the engineering knowledge persisted imperfectly. Later civilizations built canals, but not always as well. Medieval Islamic engineers in Iraq constructed impressive waterworks, but they also marvelled at ancient canals whose construction techniques they couldn't fully replicate. Knowledge eroded. The capability survived, but not at earlier levels. Later engineers could move water, but not always with the precision or scale their predecessors achieved. The difference between fully understanding principles and approximately copying predecessors' work is subtle but significant. One produces innovation, the other produces competent imitation that degrades slowly across generations. What the Mesopotamian hydraulic record shows is that large-scale civil engineering appeared early and declined gradually. The peak of achievement came in 3rd millennium canals and 2nd millennium waterworks. Later periods maintained some systems but struggled to match earlier construction quality. By the 1st millennium BC, references to ancient canals suggest awareness that current capabilities didn't match the past. Water shaped civilization, and civilization shaped water's flow in turn. But that shaping required knowledge that appeared remarkably early, functioned brilliantly for millennia, and then partially faded, leaving traces in abandoned canal beds and fragmentary texts describing hydraulic achievements modern engineers examine with respect and puzzlement, wondering how ancient engineers, with supposedly primitive tools, achieved results that still impress 4,000 years later, before the flood. The well-Blundell prism sits in the Ashmolean Museum at Oxford, a clay prism approximately 20 centimetres tall, inscribed on all 4 sides with cuneiform text. Catalogue number WB 444. Dating to approximately 1800 BC, it preserves the Sumerian king list, a chronological compilation of rulers from the dawn of kingship to the scribe's own time. And it begins with a phrase that appears repeatedly in Mesopotamian literature. After the kingship descended from heaven, the kingship was in Eridu. Then it lists the kings of Eridu before the flood. 8 rulers. Their reign lengths are staggering: 28,800 years, 36,000 years, 43,200 years. Impossible durations, obviously symbolic or calculated, using numerical systems whose logic is opaque. But the text presents them as historical, not mythological, part of the same continuous list that includes historically verified rulers from later periods. After the 8th antediluvian king, the text states these are 5 cities, 8 kings ruled for 241,200 years. Then the flood swept over, and after the flood, kingship descended again, this time to Kish. The post-diluvian rulers have more plausible reign lengths, decades rather than millennia, though early post-flood reigns still show inflated numbers that gradually normalise in later periods. By the time the list reaches rulers contemporary with the prism's creation, reign lengths match historical records. What is this list? Mythology dressed as history? History distorted by time? Or something else? Perhaps genuine record keeping using numerical conventions we don't fully understand. Scholars generally treat the antediluvian section as mythological, the impossible reign lengths proving that these aren't historical figures. But the Sumerians themselves made no such distinction. They recorded antediluvian and post-diluvian rulers in identical formats, using the same formulaic language in became king, he ruled. The text structure doesn't signal mythology versus history. It presents continuous chronology interrupted by a single catastrophic event, the flood. And the flood itself appears throughout Mesopotamian literature as historical event, not merely myth. The Epic of Gilgamesh contains extensive flood narrative. The gods decide to destroy humanity. Utnapishtim is warned to build a boat. He saves his family and animals. The flood covers the earth. The boat grounds on a mountain. Humanity survives. This story predates the biblical Noah account by over 1,000 years. But Gilgamesh isn't the only source. The Sumerian poem Eridu Genesis tells a similar story. The Atrahasis epic from the Old Babylonian period describes the flood in detail. Multiple independent texts reference this event, suggesting it held central importance in Mesopotamian historical consciousness. Could it preserve memory of actual catastrophic flooding? Mesopotamia experienced regular floods. Severe floods occurred periodically, devastating cities and displacing populations. Archaeological evidence shows flood layers at several Sumerian sites, thick bands of clean silt interrupting occupation layers, indicating major inundations that temporarily abandoned settlements. But none of these flood layers align chronologically across all sites. They're local floods, each affecting individual cities at different times. There's no geological evidence for a single catastrophic flood that inundated all of Mesopotamia simultaneously. The flood described in the myths is universal, covering the entire world, destroying all civilization except one family. That didn't happen. So what are the flood stories preserving? Perhaps the texts amalgamate multiple devastating floods into single mythological event. Perhaps they exaggerate a severe but not universal flood that destroyed enough cities to seem world-ending to survivors. Or perhaps they preserve memory of events from before Mesopotamian civilization began, events that predated writing, transmitted orally for millennia before being recorded in cuneiform. That last possibility is intriguing because the Sumerian king list explicitly states that kingship existed before the flood. It claims antediluvian civilization, with cities, rulers, and institutions. After the flood, kingship descended again, and civilization resumed. The text presents the flood not as ending prehistory, but as interrupting history, breaking continuous civilization into before and after periods. Other tablets reference before the flood as temporal marker. Medical texts copied in the first millennium BC include colophons stating from tablets written before the flood. Astronomical observations cite data from the time before the flood. These aren't mythological references. They're chronological markers, used the way we'd say before the Common Era, locating events in time relative to known reference point. Did the scribes believe these were literally antediluvian, or was before the flood simply a phrase meaning very ancient, the way we say since time immemorial without meaning it literally? It's difficult to determine, but the usage suggests the scribes treated the flood as real historical boundary, even if its details had become mythologized. The antediluvian king list poses another puzzle. Why 5 cities? Eridu, Bad Tabira, Larak, Sippar, and Shuruppak. These cities were real places, excavated archaeologically, some with occupation layers reaching back to 5000 BC or earlier. The king list claims they existed before the flood and survived it, continuing into the post-diluvian period. Is this historical or legendary? Eridu holds special significance. It's consistently named as the first city where kingship first descended. Archaeological work at Eridu reveals occupation from the Ubaid period, circa 5400 BC, with temple structures from very early periods. It was a major religious centre, sacred to Enki, god of wisdom and fresh water. The city's antiquity and religious importance may have led to its placement at civilization's beginning in the king list. But why connect it to pre-flood times? Perhaps because Eridu was genuinely ancient by Sumerian standards, a city already old when other cities began, its origins lost in preliterate times. Calling it antediluvian might be a way of expressing older than our records can trace. Or perhaps the text preserves something else. What if Sumerian civilization wasn't the beginning? What if the Sumerians themselves inherited cities, techniques, and knowledge from earlier cultures whose historical records didn't survive? The sudden appearance of sophisticated Sumerian civilization around 3200 BC, with writing, mathematics, astronomy, and engineering seemingly emerging fully formed, might indicate not invention, but inheritance. If an earlier civilization existed in Mesopotamia before Sumerian times, it left minimal archaeological traces. We find continuity from Ubaid to Uruk periods, gradual development of pottery styles and architecture. But would we recognize fundamental technological shifts if they occurred? If knowledge was transmitted orally or through practices that left no physical trace, earlier achievements would be invisible in the archaeological record. This speculation goes beyond evidence. No confirmed archaeological material demonstrates sophisticated pre-Sumerian civilization, but the absence isn't conclusive. Much of southern Iraq remains unexcavated. Rising water tables and millennia of sediment accumulation bury earlier periods deep. Archaeological sampling is sparse. It's possible, though unproven, that earlier developments existed beneath layers we haven't reached. What we do have is the Sumerians' own claim that their knowledge came from before, from the gods, from ancient times, from teachers who predated their civilization. They never claimed to have invented what they knew. They framed themselves as preservers and transmitters. The flood narratives might be cultural memory of catastrophic transition, not necessarily literal deluge, but civilizational collapse that destroyed centers of learning and forced survivors to rebuild with fragmentary knowledge. If an earlier culture had developed sophisticated capabilities, then collapsed catastrophically, survivors would preserve what they could. Over centuries, the disaster would become mythologized as the flood, and the earlier civilization would become the antediluvian age. This reading makes the king list not mythology but distorted history, genuine chronology whose earliest sections have been corrupted by time and oral transmission into impossible numbers and legendary details. The core claim that civilization existed before a catastrophic break would be true, even if the details had become mythological. But we can't prove this. The texts are ambiguous. The archaeology is incomplete. The flood might be myth, or exaggerated history, or garbled memory of something we haven't yet understood. What's certain is that the Mesopotamians themselves treated it as real, referenced it consistently, and structured their chronology around it as pivotal event. And if they were wrong, if the flood was purely mythological, then their entire framework of inheriting knowledge from earlier times collapses. Their sophisticated capabilities must have developed within Sumerian civilization itself. Across the brief centuries from 3500 to 3000 BC, without the antediluvian precursors their texts claimed. But if they were right, if something existed before and then catastrophically ended, then the sophisticated knowledge appearing in early Sumerian texts makes different sense. They weren't inventors starting from scratch. They were survivors preserving fragments, restoring what they could remember, maintaining traditions inherited from teachers whose names and stories had faded into divine mythology, but whose knowledge survived as practical techniques passed generation to generation, copied into cuneiform tablets, by scribes who understood they were preserving something far older than their own civilization. The pattern of inheritance. Language reveals assumptions. When we describe historical developments, we use the vocabulary of innovation, invention, discovery, development, advancement. These words imply humans creating new knowledge through ingenuity and experimentation. They assume progress begins from simpler states and builds toward complexity. But Sumerian tablets rarely use such language. When describing knowledge, they employ different terminology. Texts speak of receiving wisdom, of preserving ancient formulas, of restoring what was known in earlier times. They frame knowledge not as human achievement, but as inheritance from divine teachers or recovery of lost understanding. This linguistic pattern appears consistently across genres. Mathematical tablets don't celebrate discovering new techniques. They present calculations as established procedures, sometimes noting they follow the ancient method. Medical texts reference treatments from the time of the ancestors. Astronomical tablets cite observations recorded in former times. Even when scribes composed new works, they often attributed authorship to gods or legendary sages rather than claiming personal credit. The Enuma Elish creation epic doesn't identify a human author. The Code of Hammurabi presents laws as given by the gods, with Hammurabi as implementer rather than originator. Wisdom literature attributes sayings to ancient sages whose historicity is uncertain. This might be simple cultural humility or religious convention requiring divine attribution for important knowledge. But the pattern is pervasive enough to suggest something deeper, a fundamentally different conception of knowledge's nature and origin. Modern Western culture, shaped by Enlightenment emphasis on progress and individual genius, assumes knowledge grows through human effort. We celebrate inventors and discoverers, naming laws and theories after their originators. We construct narratives of advancement, from ignorance to understanding, from primitive to sophisticated, from ancient simplicity to modern complexity. But what if Sumerian culture operated on different assumptions? What if they genuinely believed humanity's knowledge came from external sources and their role was preservation rather than invention? Their texts consistently present this view. They describe knowledge as gift, requiring careful maintenance lest it be lost. This perspective has profound implications. If you believe knowledge comes from inheritance rather than invention, you'll prioritize preservation over innovation. You'll copy old tablets exactly, even when you don't fully understand them, because the ancients who wrote them knew more. You'll resist changing traditional procedures, since alterations might corrupt inherited wisdom. You'll view yourself as custodian of knowledge, not creator of it. And this is exactly what Mesopotamian scribal culture did. They copied tablets meticulously across centuries. They preserved texts whose language had become archaic. They maintained procedures they practiced but hadn't invented. They treated written knowledge as precious inheritance requiring protection. This conservatism had advantages and costs. On the positive side, it preserved tremendous information. Knowledge that might otherwise have been lost in catastrophes survived because scribes maintained multiple copies across different cities. Mathematical techniques, medical treatments, astronomical data all survived because preservation was cultural priority. On the negative side, conservatism resisted innovation. When practitioners did develop improvements, they might not record them as such, instead presenting novelties as recovered ancient knowledge or divine revelation. The scribal system maintained existing knowledge efficiently, but incorporated new knowledge slowly and awkwardly. Yet, innovation did occur. Mesopotamian civilization developed across millennia. New technologies appeared, new texts were composed, new capabilities emerged. But the culture framed innovation conservatively, embedding novelty within traditional structures. New mathematical techniques might be presented as restoring the ancient method. New medical treatments might be attributed to divine revelation in dreams. New astronomical observations would be incorporated into traditional compendiums. This creates interpretive challenges for modern historians. When a tablet claims to preserve ancient knowledge, Is it genuinely copying older material, or is it presenting contemporary developments as traditional? When a text attributes knowledge to gods or legendary sages, does it preserve actual memory of earlier teachers, or is it simply conventional authorship attribution? We can't always determine this from texts alone. Some tablets can be dated paleographically, earlier writing styles versus later ones, allowing us to identify when texts were actually composed versus when they claim to originate. This reveals some ancient texts are actually later compositions, suggesting the culture sometimes created new material while presenting it as traditional. But other texts genuinely are old. Medical tablets from the 3rd millennium reference treatments still used in the 1st millennium. Mathematical techniques from Old Babylonian period continue in Neo-Babylonian texts. Astronomical observation methods remain consistent across centuries. Some knowledge really was inherited across vast time spans, copied and recopied by scribes who faithfully maintained what their predecessors had recorded. This creates a mixed picture, genuine inheritance of ancient knowledge combined with cultural tendency to frame everything as traditional, making it difficult to distinguish real antiquity from constructed antiquity. Both patterns exist simultaneously in the textual record. What's crucial is that the Mesopotamians themselves believed in knowledge inheritance. Whether or not specific texts were genuinely ancient, the culture operated on the assumption that wisdom came from earlier times and required preservation. This belief shaped their institutions, scribal schools teaching copy precision, libraries maintaining extensive tablet collections, temples supporting scholarly communities across generations. And this belief may reflect actual experience. In a civilization that repeatedly suffered catastrophic disruptions, wars, floods, economic collapses, invasions, knowledge loss was real and visible. Each disaster destroyed libraries and scattered scholars. Recovery required finding surviving texts and reconstituting understanding. Scribes repeatedly experienced knowledge as fragile inheritance, requiring active maintenance. Living through such cycles would naturally produce culture emphasizing preservation. When you've seen knowledge lost and painstakingly recovered, you understand it's not inevitable or automatically progressive. It's contingent, requiring deliberate effort to maintain. This produces conservatism not as theoretical position, but as practical wisdom. The linguistic pattern of inheritance language, then, might be less about theological claims regarding divine knowledge sources and more about practical recognition that knowledge comes from the past, transmitted through teaching and text, maintained only through continuous effort. Each generation inherits understanding from teachers and texts, adds what it learns through experience, and passes the augmented corpus to the next generation. But the core flow is temporal, knowledge moving forward through time, preserved by conscious transmission. This makes the Mesopotamian view of knowledge less alien than it initially appears. They simply emphasized the inheritance dimension we often neglect. We focus on innovation and progress. They focused on transmission and preservation. Both dimensions are real. Knowledge does grow through new discoveries, and knowledge does require transmission from those who know to those learning. Different cultures emphasize different aspects of this dual reality, but the Mesopotamian emphasis on inheritance raises the question, inherited from whom, ultimately? Tracing backward through the centuries of cuneiform tablets, we reach the origins of writing around 3200 BC. But the knowledge recorded in those earliest tablets, mathematics, administration, astronomy, was already sophisticated. It didn't start from zero. So where did it come from? The tablets claim from the gods, from ancient times, from before. And while modern scholars reject literal divine knowledge gifts, the claim that knowledge came from earlier times might be accurate. Perhaps the Sumerians, who first pressed cuneiform into clay, were recording knowledge that already existed in preliterate forms oral traditions, practical techniques, accumulated wisdom from centuries or millennia before writing emerged? If so, then the pattern of inheritance the tablets explicitly describe actually extends deeper than the tablets themselves. The written tradition preserves and transmits knowledge that began before writing, making the entire cuneiform corpus an extended project of inheritance maintenance, a 3,000-year effort to preserve and pass forward wisdom whose ultimate origins had already been forgotten when the first tablets were inscribed. What we choose to remember. The last cuneiform tablets were written in the 1st century AD, over 3,000 years after the script's invention. By then, alphabetic writing had long since supplanted wedge-shaped signs, and cuneiform survived only in temple contexts, maintained by conservative priestly communities. When those final scribes died, the knowledge of reading cuneiform died with them. For nearly 2 millennia, countless tablets lay buried and unread, their contents silent. What finally disappeared wasn't the tablets themselves. Clay survives magnificently, but the understanding to read them, the physical records endured, while the intellectual tradition that created them vanished. This is the paradox of preserved knowledge. Having information isn't the same as understanding it. Storage isn't transmission. The tablets existed continuously from their creation to their excavation, but their meaning was lost for 2,000 years because the living chain of teachers and students broke. When 19th century scholars finally rediscovered how to read cuneiform, they recovered vast knowledge, but not everything. Some tablets remain untranslated, damaged, fragmentary, or written in poorly understood dialects. Others have been translated, but not fully comprehended. We know what words they contain, but not necessarily what they mean. Still, others were surely lost entirely, tablets destroyed, crumbled, or never excavated. What we know of Mesopotamian civilization comes from perhaps 1% of tablets that originally existed. Thousands survive, yes, but millions were created across 3 millennia. Most are gone, and what survives is biased. Administrative records and royal inscriptions' durability meant they were fired and stored carefully. Personal letters, teaching materials, technical workshop notes, the everyday ephemera of lived experience, these were less carefully preserved and have largely vanished. So we're looking at civilization through a filtered lens. We see what accidents of preservation and archaeology recovered, not a representative sample. We see what Mesopotamians chose to write down, not everything they knew. We see texts without the oral context that accompanied them, knowledge stripped from the social structures that maintained it. This makes all historical claims about ancient knowledge provisional. When we say Sumerian mathematics was sophisticated, we mean the mathematical tablets we've found show sophistication. Perhaps other texts, now lost, showed even greater achievements, or perhaps the tablets we have represent the peak, with typical practice being simpler. We can't know what we haven't found, but what we have found is remarkable enough. The Plimpton 322 tablet that opened this exploration with its accurate calculation of the square root of 2, the Nippur Pharmacopoeia with its chemical formulas, the astronomical tablets tracking centuries of observations, the medical texts describing surgical procedures, the metallurgical recipes specifying alloys, the canal systems engineered at civilization scale. All of this existed, was created, was used, and was recorded by people living 4,000 years ago. And much of it was subsequently lost, not the tablets, but the understanding. Later Mesopotamian scribes copied texts they couldn't fully comprehend. Medieval Islamic scholars excavating ruins found tablets they couldn't read. The knowledge embedded in these texts became inaccessible despite physical survival. This teaches us something important. Knowledge exists in minds, not merely in records. Books don't contain knowledge so much as encode it. To extract knowledge from text requires readers who already possess significant understanding. A physics textbook is useless to someone who doesn't know mathematics. A medical text is meaningless without anatomical knowledge. Advanced information builds on foundational understanding. Without the foundation, the advanced material is just symbols. When Mesopotamian civilization collapsed, taking with it the educational systems that maintained foundational knowledge, even preserved texts became partially opaque. Later readers could decode words, but missed meanings that would have been obvious to educated contemporaries. Subtle distinctions in terminology were lost. Contextual assumptions scribes didn't bother stating were forgotten. The written legacy survived but degraded, its full richness reduced to what later periods could reconstruct from fragmentary evidence. We face the same limitation today. We've recovered cuneiform literacy, but we're not native cuneiform readers. We've learned the language the way we learn foreign languages, systematically but not immersively. We miss nuances, struggle with ambiguities, argue over interpretations that ancient readers would have found obvious. We approach these texts as outsiders, which means we inevitably misunderstand some content. This humbles any claims about what ancients knew or didn't know. Our understanding is necessarily incomplete. We work with partial data, filtered through preservation biases, translated across linguistic and cultural gulfs, interpreted through our own assumptions. We're reconstructing a civilization from fragments, which means our reconstructions are provisional, subject to revision as new evidence emerges or new interpretations gain acceptance. But even with these limitations, certain conclusions seem secure. Ancient Mesopotamians developed sophisticated knowledge in multiple domains. They were capable, intelligent, creative people who observed carefully, experimented systematically, and transmitted what they learned across generations. They built civilization not through divine intervention or alien assistance, but through human effort applied consistently over millennia. Yet they also saw themselves as inheritors. Their texts consistently frame knowledge as received rather than invented, as preserved rather than originated. Whether this reflects genuine historical memory of inheriting from earlier cultures, or simply represents cultural humility, or perhaps captures something true about all knowledge, that it's always inherited, always transmitted, never truly created ex nihilo by individuals, remains open to interpretation. What's certain is that much was lost. Capabilities documented in 3rd millennium tablets disappeared from later records. Techniques described in one period weren't practiced in the next. Knowledge eroded despite efforts to preserve it. The Mesopotamian scribes, despite their dedication to copying and maintaining texts, couldn't prevent gradual knowledge loss across centuries of disruption and decline. This raises uncomfortable questions about our own civilization. We trust that knowledge, once gained, is permanent, that scientific discoveries and technological capabilities, once achieved, won't be lost. We assume progress is directional and irreversible, but Mesopotamian history suggests otherwise. It shows that knowledge can be lost as readily as gained, that capabilities can vanish despite being recorded, that civilizational decline can erase understanding even when physical texts survive. We preserve information far more extensively than ancient peoples could. We have redundant storage, global distribution, digital backups, but we also depend on complex infrastructure to access that information. Digital archives require functioning computers, electricity, and software to decode data. If those systems failed catastrophically, much of our preserved information would become instantly inaccessible, even though it physically exists on drives and servers. The Mesopotamian tablets, by contrast, are readable with just light and language knowledge. Their technology is robust, clay endures, cuneiform is decipherable with dedicated effort. Yet the civilization that produced them still lost the knowledge, not through infrastructure failure, but through social disruption breaking the chains of transmission. Both preservation strategies have vulnerabilities. Physical durability doesn't guarantee understanding. Digital redundancy doesn't guarantee accessibility. Knowledge persists only when living people maintain the capacity to understand and use it. This requires stable institutions, continuous education, and social priority given to learning and transmission. When these break down, knowledge evaporates with shocking speed. The Sumerian tablets are monuments to both human achievement and its fragility. They show us what's possible, that ancient peoples with supposedly primitive tools developed profound understanding. And they show us what's at stake, that knowledge hard won over centuries can be lost in generations, leaving only artifacts and descriptions that later peoples struggle to interpret. As we move through our own time of rapid change, with technologies developing faster than institutions can adapt, with social disruptions challenging traditional knowledge transmission, with environmental pressures threatening stability, the Mesopotamian example offers warning and hope. Warning that knowledge is vulnerable, that progress isn't guaranteed, that civilization can decline as readily as advance, but also hope that human ingenuity and dedication can achieve remarkable things, that knowledge preserved across millennia can be recovered, that even after catastrophic breaks, later civilizations can reconnect with earlier achievements. The tablets themselves endure, pressed clay holding the marks of hands that crumbled to dust 4,000 years ago. They wait in museum drawers and archaeological storage rooms, countless more still buried beneath Iraqi soil, patient repositories of knowledge inscribed by scribes who hoped, probably without thinking about it explicitly, that what they wrote would outlive them. It has. We read their words. We struggle with their meaning. We marvel at their achievements. We recognize in them something fundamental, the human drive to know, to understand, to preserve understanding for others. That drive created cuneiform, filled tablets, built libraries, transmitted knowledge across countless generations of teachers and students. And that drive persists in us, reading these tablets, trying to understand what they reveal about both ancient capabilities and the patterns of knowledge, how it's created, transmitted, preserved, and lost. The scribes who pressed styluses into wet clay couldn't imagine us, thousands of years later, carefully translating their work. But they wrote as if someone would read, as if meaning would persist, as if knowledge mattered enough to preserve. They were right. Their knowledge survived. Not completely, not perfectly, but substantially. Enough that we can recognize them as intellectual kin, struggling as we struggle to understand their world and preserve what they learned for whoever comes next. The chain continues, linking us to them, linking future readers to us, an unbroken thread of transmission stretching across millennia, fragile but enduring, carrying forward the accumulated understanding that defines human civilization. The tablets say, we learned, we knew, we preserved what we could. And we read them now, learning what they knew, struggling to preserve it in turn, adding what we learned to the corpus, hoping our descendants will also read, understand and carry forward knowledge we've tried to save. This is inheritance. This is transmission. This is how human understanding survives time's erosion. Not automatically, not easily, but through deliberate effort, generation after generation, choosing to remember what matters, choosing to preserve what we've learnt, choosing to teach what we know. The Sumerian tablets reveal ancient inventions erased from history, yes, but more fundamentally, they reveal knowledge itself as human inheritance, precious and fragile, requiring active maintenance across generations to survive. What they learned and what they lost, what they preserved and what vanished, tells us as much about knowledge's nature as about ancient capabilities. And in the quiet of museums, storage rooms and archaeological sites, those tablets wait, holding still more secrets we haven't yet extracted, more knowledge we haven't yet recovered, patient fragments of a civilization that achieved remarkable things, then passed most of them, but not all, to whoever came next. We came next. We're reading now. And what we choose to do with what they preserved will determine what survives for whoever reads after us.